calling coronavirus the China virus is not racist.
Okay, I'm live. Hello. Got one person. Who is that? 3. Outstanding. Hello, how's everybody? All right, so we're gonna finish up this section 6.3. I know it's seems like we've been doing it forever. Okay, so we're gonna finish up binomial distribution, GMS. GMS is not gonna take long. Okay, so we got 9 people, so we'll wait a few more minutes. But if your discrete random variable, which we did yesterday, if your discrete random variable table is binomial, then you don't have to do the use of formula for that your outcome times your probability of standard outcome for all of them and sum them up. If it's a binomial distribution, you simply have to do this. That's it. All right, so Mr. Joseph called, so we're gonna wrap this up by 2:30. So we need to get going. All right, for the people it's 10 of us on here, we're just gonna go for 10 right now. People that come in a little later they'll just have to watch it later. But I don't wanna take away from Mr. Joseph's time. Okay. All right, so again, yesterday when we did the discrete random variable table, we did it the long way, but if it's binomial, we can always use this to find the mean, the expected mean and expected standard deviation. Okay, now we want to talk about, we're going to talk about the 10% condition rule. All right, so what that means is, and we're going to use again, we're building on this, so we're going to use this for the rest of the semester. Okay, so basically what they're saying is, okay, N, so N is going to be, capital N is your population. Okay, we know that lowercase n is going to be your sample. All right, so in order for you to, and this is also your independence rule. That's your 10% condition rule. So what's that mean is, remember we talked about earlier that you don't want your sample size to be no more than 10% of your population. Okay, so that's what this rule is for. You can write it like this, or you can write it like this. Both. So this is your 10% condition rule, and your 10% condition rule guarantees that you're going to have independence in your data, that your data is independent of each other. So you always, if you're going to pick your sample size, it has to be 10% of the population or less, because once you go past 10%, your data becomes less independent. Okay. All right. So any questions on this? Oh, and this rule is on page 394. Okay, outstanding. All right, so we got the 10% condition rule. All right, so if your data is binomial and you got the 10% condition rule, and another thing we have to do is we got another rule of thumb we're going to talk about in just a second. If that's the case, you can use the norm curve to approximate your data. Okay, so I'm going to take this off. I guess I can put it here. I'm going to put the 10% condition. All right, so now you can use so if you're gonna use your binomial, we can use this to find the mean and the standard deviation. You're gonna look at the 10% condition rule for independence, and then independence binomial talk about independence, but we're gonna talk. But you want your sample size to be no more than 10% of your population, and then if your sample size times your success is greater than or equal to 10, and at the same time your sample size in your failure is greater than or equal to 10. If that's the case, you could use your norm curve. So if that's the case, then norm curve now becomes n times p, and the square root of n times p 1 minus p is going to be your standard deviation for your norm curve. There. Hello, Abby. All right. So we got discrete random variable. Table is binomial. We can use these formulas. We want to include the 10% condition rule. And then if your sample size times success and the sample size times your failure, if they're both is greater than equal to 10, then we can use the norm curve to find that data. Okay, so that's basically it for binomial distribution. So I'm gonna leave this up here so you can write it down. Then we'll actually do a problem. Oh, and this information is on page 395. We're good? Wait for a response. All right, Gabrielle, thank you. All right, so I'm going to erase this, and we're going to use a formula. We're going to solve a problem. So with this, we're gonna find this probability. All right, so to find the mean, since it's a binomial distribution, so that means the mean of x is simply going to be 2,500 times 0.6. And so that's going to give me 1,500. Now to find the expected mean, we're going to take the square root of, so this is n times p. Then for this, up under here, we're going to do what? N times p times 1 minus p. All right, so in that case, n times p is 1,500. And since our success was 60%, that means our failure is 40%. So now we're going to define, so now we want to do 40% of 1,500. All right, so that's going to be 600. All right, we're good? So if we have this, so now we have 1,500, 600, mean standard deviation. All right, so no, remember, look, we got to do the square root of n times p times 1 minus p. Remember, p is equal to 0.6. So we got to put up on the, so this is n times p, and this is 1 minus p. All right, so let me check. Maybe I did something wrong. Okay, so, oh, so yeah, you're right. You're right. It's the square root of that. You're right. So I should have did this. Sorry about that. So we got to do the square root of 60. We got to do the square root of that. I'm sorry. So it should be 24 point. We could just do 5, can't we? Well, 49. 49, 49. Sorry about that. All right. So this is our standard. So this is going to be our standard deviation. So I should have put 600 up under here. So that's my bad. So now we should have 24.4949. So that's right, Brianna. Okay, there we go. My bad. All right, now. So now we got to check to see. So we do n times p. We know that's going to be 1,500. Then if we do n times 1 minus p, that's simply just going to be 2,500 minus 1,500, which is 1,000. Because if you think about it, if the sample size is 2,500, right? And then we're going to multiply that by 0.4. And that should give us 1,000. The reason why you would simply subtract, because you need the total sample size. So if n times p is 1,500, then what's left over? It's going to be 1,000. So I'm going to write up here the norm curve. Now that I know that this is true, so this is greater than or equal to 10, and this is greater than or equal to 10. So if that's the case, that means this, I could use the norm curve to solve this. So now I have 1,500, and I have what, 24, 49, 49. So that's the expected mean. That's expected standard deviation. And I can use it for the norm curve. Now, if we want to check the 10% condition rule, this problem was based on United States citizens. So we know if this is 2,500, we know we have more than 25,000 U.S. citizens. Okay. So n times. So we got. So we know that we can use the norm curve because these two facts are true. Oh, because your entire population is 2,500, right? So if I take, so you can think about it this way: 60% of 2,500 is 1,500. Is a 40% left over? So 40% of 2,500 is 1,000. So 1,000 plus 1,500 is 2,500. What's the total sample size? All right, you're welcome anytime. All right, now we want to see, so we got to find the probability that the outcome is greater than 1,500. Now, if we were just a binomial distribution, it'd be a discrete random variable. We'll just have to do 0 through 1520. But since these conditions are met, we can go ahead and use the norm curve. All right. So what we want to do here, since we found that these are true, so what we want to do now, we're going to do the probability. So we'll say the probability the outcome is greater than or equal to 1520. All right. So we know it's a norm curve, so we can convert this to z. Z is greater than or equal to 1520 minus 1,500, all divided by 24.4949. So that's going to be z is greater than or equal to, what's that, 20? All over 24.4949. So we're going to put that in the calculator and then approximate our percent. So what we need to do now is we're going to do 20 divided by 24.4949, and that should give us 0.82. Then we're just going to look that up on the table. All right. And so what is that? What is the probability this is going to occur? Somebody look it on the z-score table for me. Waiting for an answer. Okay, let's do this, Danielle. So we got 0.82, so that's going to be approximately about right here. And we're looking for this area right here. So if you think about it, does that look like 79%? Okay. All righty. Because remember, if it's greater than, then we look up the opposite sign. Okay, so you was right, Gabrielle, when you said it was, but remember what you wrote is going to be from the very beginning up to there. Okay, so you had what, 79.39? Now, if you drew this curve out, you knew that wasn't correct. And so we got, so what was it, 2061? And so that's your answer. So if you want to, if you go to page 396, that's where I got the example from. All right, so we are done with binomial distributions. So you got 4 rules for binomial distribution. Okay, then we talked about 10% condition rule today. Then we also talked about how you can take a binomial distribution and use and convert it to a norm curve. In order for it to be converted to a norm curve, this has to be true, and you want to be looking at the 10% condition rule. Okay, so now only thing I have to show you is binomial distribution, and we'll be done. Okay, so Mr. Joseph is waiting on us. So do anybody have questions on this one? If not, we're gonna go ahead and get geometric distribution out of the way. And I have to show you some formulas on geometric distributions that's not in the book, but it's gonna help you tremendously if you were to learn it to easily find your probability using the geometric distribution. So you're gonna do another practice problem? Okay, all right, we can. Okay. All right. So we have this problem here. So X is our outcome. So we have a random sample of 506 teenagers from 14 to 18 that has a debit card. All right. Then we want to look with the probability of having a debit card is going to be 10%. All right. And so we want to find a probability that 4 or less have a debit card. Now, and this is a binomial distribution. So we already checked the 4 rules. The 4 rules, what? Fair, success, independent. So we got to check for independence, and we have all of them have same probable success, and this is the fixed number 506. All right, so we're going to test the 10% condition rule. So 10% condition rule, so if n is equal to 506, then we want the population to be at least 506 times 10. So the population needs to be at least 5,060 14 to 18-year-old teens with debit cards. And so that's going to be your 10% condition rule. And we're going to use this from now on. And so again, this is your independence. They're not saying it now, but later on, it's going to be your independence rule. We're going to try to be done before 2:15. It's not going to take long. Once we do this problem, I'm going to show you how to do geometric distribution, and that's not going to take long. We'll be done. We'll be done. Give me what? Less than 20 minutes. We'll be done. All right. So now we did the 10% condition rule. For now, we got to test for normality. In other words, to see if we can use the norm curve. All right, so if that's the case, we're going to do n times p is greater than or equal to 10. And we have to do n times 1 minus p is greater than or equal to 10. All right, so in that case, we're going to do what, 500? 506 times 0.10, and that's going to give us 50.6. And so now we're going to do 506 times 0.9, and then that's going to give us what? Why am I picking up a calculator to do this? I feel ashamed. Okay, so 455.4. But we know if we talk about real time, this could be 51 students, and this would be 455 students. So this rule is being held, this rule is being held, and this rule holds. All right. So now with this sample size, probability of success, the 10% condition rule is being met. Okay, normality rule is being met. Now, so that means we have now we can find the mean and the standard deviation. So the mean for this is just going to be, isn't this the mean? N times P. All right, so now the standard deviation for this is the square root of 50.6 times 0.9. And then that's just going to give us the square root of, what's that? 455.4. And then that's going to give us 21.3401. Okay. So you said never mind, so you get why it's the 10% condition rule? Okay. No, it's what I'm gonna do with y'all, man? It's N. How you gonna do 50.6? This is N times P. N is 500. It's N times 1 minus P. Come on, Bree, you better than that. You better than that. These are the rules. It's N times P and N times 1 minus P. That's it. All right. So the 10% condition rule is being met. We just found we just test for normality. So the normality rules are being met. So we can use the norm curve to solve this problem. Oh, yeah, you're right. You're right. Bray, I'm sorry, you're right. Go up on the here. So you're right for that one. So that's going to be 50.6. And I'm sorry, you're right. Okay, times 0.9. And then that's going to be 6.7. What's that? 483. So you're right, Bree. You're right. I'm sorry. All right, so we're looking for the probability. So we'll just go to Z. So Z is going to be less than or equal to what we're looking for, 40. And then we're going to do the mean was 50.6. All that is divided by 6.7483. Then the probability of Z is less than or equal to, so let's find that number. Did y'all find it already? Yeah, this is right. 6 point. Yeah. Yeah, that's right. This is right. So this should be 50. So this right here, Brianna was right. It had to be up on the router. So this is the answer. Okay, now we want to find so we got 40 minus 50.6 divided by 6.7483. So now that's going to give us a negative 1.57. Then we're going to look that up. Okay. So we got a negative 1.57. And so what's the probability that's going to occur? It's over here. I wrote that in the very beginning, Brianna. I mean, Gabrielle. I wrote that in the very beginning. Okay, so yes. So your answer is going to be 0.0582. And thank you, Abina. I appreciate it. Because remember, if it's less than, we're going to come here, and then this is going to be 0, 1, 2, 3. And this is going to be a negative 1, negative 2, and negative 3. And so we're looking for a negative 1.57. That is going to be this little area right here. And so that's why this makes sense. And I do apologize for not catching this, but I'm trying to hurry and get it done so you can get to Mr. I didn't know I was taking up Mr. Joseph time. And so I'm trying to hurry and get this done. And I thank you for catching that. So, any other questions on this? Because I want to finish this up. So tomorrow, I just want you to do the book work. So only thing we're doing tomorrow is answering any question you may have for the problems for today. That's on the blog for that section. Okay. And then I'm just going to be asking those questions. And then I'll give you the practice test. And then I'll just let you work on that over the weekend. So we won't meet Friday. Because remember, I said that was my anniversary. And I love teaching y'all, but my wife is more important. Now, all right, so let's keep it moving. Now we got to do geometric distribution. All right, so let's go ahead and get this out of the way. Oh, there you go. He's quiet today. All right. Well, I'm giving these markers pure D. All right. So you have 4 rules for geometric distribution. All right. You want a failure or success. You want it to be independent. You want each trial probability to be so these are the same rules for the 3 rules that we have for binomial distribution. Only difference between geometric, we're going to do until there all right. So your geometric distribution, you do it until there's success. In other words, you know how I talked about if you take a test, if I give you 2 chances to pass it, you take the first time, you don't do well, you fail, you redo the test, and you pass it. That's it. You got a fixed amount of times you can do it. That's twice. But geometric, you're gonna do it until you get a success. It means some people I may give you 4 tries to take the test. I'll give you 5. Just do it until you pass the test. That's a geometric distribution. I'm not gonna do that, but I'm just saying. Okay, now. Oh, how we do an actual test. Okay, so for your rules for geometric, so in other words, so for example, only thing you have to do, know how we did the individual probabilities for a binomial? Geometric, this is your formula. We'll get to that. You'll get tested. No, it's going to cover the whole entire chapter. That's what the test is going to cover. We're going to do one with me, and we're going to do one with the AP online. We could do both. We could do both of them. So you tell me, do you want a test and a test count for a test and a quiz, or you want to do a quiz and a test? Well, I'll keep you informed. Just make sure you stay on your remind. Okay, so remember, for a geometric distribution, it doesn't count until you get a success. So if you get just all failures, it doesn't count because it does not count until you get a success. So that's why your probability is equal to 1. All right, let's say that we have success is going to be 40%. All right, and we're going to say, well, it's going to take 3 tries to get it done. So this is what, so now this is just for individual, and that's the only thing they have in your book. But I'm going to show you how to find the individual. I'm going to show you how to do greater than, and I'm going to show you how to do less than or equal to. It's not in the book, but I have a formula for it. It used to be in the old books. I don't know why they took it out. Okay, so what you want to do, if you think about it, we're trying to find a probability you have it take you exactly 3 times to have a success. All right, so how many failures do you have before that third success? That's the question. I can wait. Somebody need to type it in there. If it take you 3 times for a success, yep. So what you want to do, your first 2 is a failure, right? So 1 minus P is going to equal to 0.6. So you have a 60% chance that you're going to fail. That's the first time. First time you try it. Then the second time you try it, you have a failure as well. Okay, so then the third time that success comes. So that's why you're going to do, and it's independent. So if it's independent, we know we're going to multiply. So you're simply going to do, so that's why this is what your success, what you're looking for. So, but you got those 2 failures before that third success. All right, so now the problem that's going to occur is going to be calculator. So that's going to be 0.6 raised to the second times 0.4. So that probability is going to be 0.144. Girl, if you don't stop your third success, don't you have to fail twice? If they're independent, don't you multiply your fail? If they're independent, you got a failure the first time, a failure the second time, the third time, you're going to get your success. They're independent. Don't you multiply? Independent means multiplication. It is 3. 1, 2, 3. Fail the first time, fail the second time, success the third time. Since it's independent, you're going to multiply all the probabilities for each one of them. You get it, Thelma? Yes, no, maybe, possibility. You got, really? Yes, you got to figure it out. You have to read the problem. And I'm gonna give you, so we're gonna do when you do the problems in the book, is you got to check and see if it's geometric. Okay. And some of the problems going to tell you it's geometric or binomial, but when you taking your stat class in college or the AP exam, you're going to have to distinguish. You got to read the problem and make sure these 4 rules are being met for it to be geometric. Oh my God. You're looking for that it takes you 3 times to get a success. What's going to happen the first 2 times? So don't you fail the first 2 times? So if it's independent, you got to multiply all the probabilities. You're going again, you're going to fail the first time, you're going to fail the second time, and you're going to succeed on your second try, on your third try, I'm sorry, your third try. But since they're independent of each other, you're going to multiply the probability assigned to the outcome. The first outcome is the first time you try it, you're going to fail. Then the second time you're going to try it, you're going to fail. Then you say, you know what? I'm going to try it. I'm going to try it that third time and gotta have a success. Since they're independent, you're going to multiply each probability. Yes, that's for binomial distribution, what she's thinking about. The formula is right here on the board. It's right here. Okay, now what's the probability that x is equal to 2? And find the probability that x is equal to 1. We'll keep it simple for you. So what's the probability that it's going to be x equals 2 and x equals 1? Yes, this is the probability right here. This is the formula. So if you want to write the formula down, so this is 3. So this will be 1 minus 0.4. And then this would be to the second power, because it said, it should be, so this should be, I'm sorry, this should be n minus 1. Should be n minus 1, my fault. So it should be n minus 1. I'm sorry, it should be n minus 1 is the formula. So I need to quit fussing. Okay, so this should be n minus 1, so that'll be 2 times 0.4. That's my fault. I truly apologize. All right, I need to fuss at Mr. Braille and not you all. Okay, so if I'm now, it should be n minus 1. That's the formula. Whew. I need to quit, but I'm not going to. I made my mistakes, but you asked me questions. But this is the formula. All right, so now let's find the probability that x is equal to 2. Who's calling me? All right, so we're going to do this one. So that should be the probability of 0.6 times 0.4, and that's good was 0.24. Then this is just going to be 0.4. All All right. So what do you notice if I start out if my first is going to be a success, that's going to be 0.4. If the second time it's going to be 0.24, the third time it's going to be 0.144. So what you think the distribution is going to be for this if I keep going? What's going to be distribution? What's going to be the shape of it? Anybody? What's going to be the shape of it? Yep, it's going to be skewed to the right no matter what the percentage is. That's why I did the binomial yesterday, because binomial distribution depends on what you put in for the percent. It's going to be skewed right or skewed left or symmetric. But for geometric, it's always going to be skewed to the right. Always. Okay. All right. So I'm going to erase this. Then I'm gonna write these formulas, and you all need to get to Mr. Joseph. All right. So if you want, so the individual probability is going to equal to P x equals K equals to 1 minus P n minus 1 times P. Or K minus 1, I'm sorry. K minus 1 times P. The probability that X is going to be greater than K, that's going to be 1 minus P raised to the K. Now, to find the probability that X is going to be less than or equal to K, that's going to just be 1 minus P raised to the K. So if you want to check that, so let's say we said the probability was equal to 0.4, and we're going to do, that's your probability. So let's look for the probability that K is equal to 5 individually. So we're going to do probability that X is equal to 5. So that's going to give us what? 0.6 raised to the 4th times 0.4. Because remember, your exponents have to equal to your sample size, and your bases have to equal to 1. So if I do this one, this is equal to 0.6 raised to the 5th. If we're going to do 5, and then if we want to do this one, 5, this would be equal to 1 minus 0.6 raised to the K. And you could check in your calculator to see if this is right. All right, so we could do 0.6 raised to the 5th. So we should get 0.07 2 7s and an 8. And then this is just simply going to be 1 minus 0.0778. And then that's going to give us now you can know how we did the binomial CDF and PDF and CDF. You can go in here, you can go and you could go and use your calculator to check. to see if these are the right answers. And you'll see that they are. All right, so that's it. We're done. So check to see if you got this is correct answer. So if you wanted to put in your calculator to see if these are right, so P is equal to 0.4 and we have K is equal to 5. All right, so if you want to do this first one, K was and it's a geometric, you want to do 5. Okay, so you could do geometric and you could do PDF, comma, I think it's going to be 5, and your probability is going to be 0.4. If you want to do the probability that X is greater than 5. Okay, so what you could do for this one, you could do 1 minus the probability that X is going to be less than or equal to S less than or equal to 5. So that's going to be your geometric, 1 minus the geometric CDF. And then you want to do 5 and 0.4. And you want to do 1 and you want to use 5. And then if you want to find the probability X is less than or equal to 5, you simply just going to do your geometric CDF 5, 0.4, 1, 5. And that'll give you those probabilities. And it should be exactly the same as these. All right, so that's it. Dr. Davis is waiting on you. I mean, Mr. Joseph is waiting on you. I'm sorry. Okay, so let me see. So if I do menu, geometric, go statistics, geometric distribution. Okay, go geometric distribution. And I have what? 5 and 0.4. Okay. Oh, 0.4. Oh, so what did I do? Oh, this is the previous problem. My bad. I was doing on a previous problem. So it should be 0.5, 1, 8 should be the answer. So if I do 0.6, so if I do geometric, so let's do if it was greater than. So I told you to do what? 1 minus menu, statistics, distribution, geometric. Okay, escape. Menu. CDF 0.4. Lower bound was 1 and 5. So that should be, what's that do? Okay, 1 minus, hold on. So let's see. So if I'm doing great, so that should be 1. So greater than 5, so that's 1. Geometric. Oh, okay, CDF. So we have 5 trials. Okay, 0.4. Okay, so for geometric distribution, you're really not going to use the mean and standard deviation. You're not going to need it because you can't use a norm curve for a geometric distribution. But if you had to find the mean of the geometric distribution, it's just 1 over p. And then if you had to find the standard deviation for that, that's just going to be 1 over, where is it? So that would be 1 minus p all divided by p squared. And so you're really not going to need this, your mean and standard deviation, because you can't use the mean and standard deviation for normality. You just can't. And you won't see this on the AP exam either. Okay. So only thing you need to know is these formulas for geometric distribution, and know that your geometric distribution is always going to be, the shape of it is always skewed to the right, because the geometric distribution goes on forever. Okay, so if you do the cumulative of geometric distribution, it'll never equal to 1, because you'll never have 100% of the data. Angela, I did that yesterday, but I'm gonna do it one more time. PDF means the individual probability. You're looking for exactly what that number is. CDF is cumulative. So you're trying to find, let's say if you want to find the probability the x is less than 5. If it's geometric, it starts at 1. So you're looking for the probability x is less than or equal to 5, is you doing the cumulative 5 plus probability of for geometric distribution. The probability is equal to 5, probability is equal to 4, probability is equal to 3, probability is equal to 2, plus the probability equals to 1. That's your cumulative, because you're adding it all up. If you're just doing a PDF, you're looking for the individual probability. Got it? All right, so we're done with section 6, chapter 6. All right, so what I want you to do is go to the blog in the section, in the problem for section 6.3. Just do the rest of it because we stopped at problem 79. Just do the rest of those problems. They're dealing with rest of binomial and rest of geometric. I tell you what, we're not going to meet tomorrow. Just work on all those problems, and then we'll meet up Friday, and I'll answer your questions. And then I'll give you the practice test for the weekend. Really, Isaiah? We're not going to get it until we get all these problems done in section 6.3, like we normally do. I'm not doing nothing different. I don't give y'all a practice test till we do all the problems in the book. I know, okay. Anyway, get to Mr. Joseph because I don't want you to be late for that. And thank you all for chiming in, the 13 of you. All right, and thanks for checking on that. I was trying to hurry get done. All right. All right, see y'all later. Bye.